Hello, I'm Andrew Barlow. I'm an application specialist with PerkinElmer in Coventry, and I'm going to discuss thresholded versus global Pearson's correlation coefficient analysis. This is Pearson's correlation coefficient, which was introduced to microscopy in '92 by Eric Manders. It looks very intimidating, but it's actually a really simple equation, and it's a great way of demonstrating a statistical relationship between two images. The numerator is the red intensity minus red average multiplied by green intensity minus green average. The denominator calculates the maximum possible product if the datasets were perfectly correlated. And so we get results between 1 and minus 1. So 1 represents a perfect correlation, 0 represents no correlation or a random distribution, and minus 1 a perfect but inverse correlation. Remember, we can get results anywhere in this range between 1 and minus 1. Manders introduced further coefficients in a paper in '93, of which the most popular and useful proved to be M1 and M2, or Mx and My as we call them in velocity. Now they do require the setting of a threshold to separate signal from background, but they're really simple. Mx is the total colocalized red intensities over the threshold divided by total red intensities over the threshold. And My is the total colocalized green intensities over the threshold divided by total green intensities over the threshold. Manders used the synthetic data sets shown here to demonstrate his colocalization coefficients. So he had a red channel and a green channel, each containing 36 Gaussian objects. He moved or deleted some of the green objects to demonstrate different degrees of colocalization. These are all 8-bit images and the background intensity is 0. We're going to go through a few examples. In the first example, all of the Gaussian objects in the red and green channels are perfectly aligned. We get a Pearson's correlation coefficient of 1, Mx of 1 and My of 1. That means all of the green intensities colocalize with red and all of the red intensities colocalize with green. In this example, all of the green Gaussian objects have been displaced, so there's no colocalization. We get quite an odd result for PCC, minus 0.034. Mx is 0 and My is 0, so that's no green intensities colocalized with red and no red intensities colocalized with green. In this example, 3/4 of the green Gaussian objects have been deleted, but the remaining 9 colocalize perfectly with 9 red Gaussian objects. So PCC is now 0.494, Mx is 1, and My is 0.25. So that means all of the green intensities are colocalized with red, and 1/4 of the red intensities are colocalized with green. So Mx and My can be completely different. The R&D team here in Coventry tried something that Manders never tried, which is to invert one of his data sets. We took the green channel and we inverted it, and we reset all the background intensities to 0. So everything above the background in this data set is inverted. And when we took this data set and analyzed it in velocity, we set the threshold to 1, and we got a result of half, which is a surprising result because this is an anti-correlated data set, and we're getting a positive result, and quite a high positive result. If you look carefully at the scatter plot, you can clearly see that this is an anti-correlated data set. So this result was a surprise. You can replicate that result with lots of anti-correlated data sets. You always get positive values for them, which led us to conclude that global measurements of Pearson's correlation coefficients are strongly biased towards the positive, and that applies to any background corrected data in which the whole image is analysed, or thresholded data in which pixels below the threshold are given an arbitrary value of 0. So the question is, how do we correct this bias towards the positive? And the answer to that is you have to make 2 changes in the calculation of PCC. Firstly, we have to exclude background pixels from the actual calculation of PCC. All those areas of background, which are 0 in both channels, they're all below the mean, so 2 negatives multiplied together will contribute positive values to the overall PCC. The second thing we have to do is exclude the background from the calculation of the mean. If we include the background, we get an unrealistically low mean, in this case 21, which means that almost everything's above the mean. If we have the more realistic mean of 105, we have a significant number of pixel values beneath that, so we're now capable of generating negative values correctly. So the question is, if we do calculate PCC in this new way, the way that allows us to generate negative correlations, what effect does it have on other data sets? So if we go back and look at the Manders synthetic data sets again, we can see what results we get. And in this case, we get a thresholded PCC value of 1, mx of 1, and my of 1. So that's the same as we got with the old method of calculating PCC. In this image pair, in which all of the green Gaussian objects are displaced, so we have no colocalization, we get a new result. We get no relationship. That's because there are no pixels over the threshold in both channels. mx and my are both 0, showing that no green and no red colocalize. Now, I think this is a much more sensible result to the one we had with the old method of calculation, where we got a small negative number. This is really clear. No relationship. There's no colocalization at all. In this image pair, in which 3/4 of the green Gaussian objects have been deleted, but the 9 that remain are perfectly colocalized with red Gaussian objects, we have a thresholded PCC of 1. mx is 1 and my is 0.25. So this is a very different result from global measurements. We've got a perfect correlation, but that perfect correlation only applies to 1/4 of the red intensities, although it does apply to all of the green intensities. So this technique is able not only to generate negative correlations, but to preserve positive ones and avoid them being diluted out by uncorrelated intensities. We have to remember the importance of mx and my though. And that's why we've implemented a thresholded version of Pearson's correlation coefficient in Velocity 5.3. Now the old version, the global version, is still there, and all the global numbers, the numbers that apply to the whole data set, I've highlighted here with a blue box. And all the thresholded statistics, all the values that depend on the threshold being set, I've highlighted here in red. So you have the choice of both, but we do recommend the thresholded for Pearson's correlation coefficient. So it's all very well getting nice results with synthetic data sets, but we need to know we're going to get good results with real data sets using this new technique. So first experiments we did were with beads. We tested a mixture of multi-spec beads in which the green and red dyes occur in the same beads, and RGB beads in which the green and red dyes occur in separate beads. So this is what the beads look like. The doubly labelled beads are yellow, and the singly labelled beads are either red or green. In the image on the red, we predominantly have doubly labelled beads. And in the image on the right, we predominantly have singly labelled beads. There's only one doubly labelled bead. On the left, we can see that thresholded PCC is 0.96. Global PCC is also quite high at 0.91. In the image on the right, only thresholded PCC remains high at 0.94. Global PCC is 0.08. But we must consider that the thresholded PCC on the right applies to only 13% of the green intensities and only 8% of the red intensities. The next thing we tried was analysis of real cells. These cells have been labelled with Herxt, which is blue and labels DNA, and MitoTracker red, which labels the mitochondria. The thresholded PCC is minus 0.231 and the global PCC is 0.145. So we've effectively generated a negative correlation with thresholded PCC. And that's the more accurate result because we really don't expect to see these dyes labelling the same structures. MX and MY are both very high because the Herxt actually labels the cytoplasm as well, although rather faintly. These cells have been labelled with a mixture of MitoTracker green and MitoTracker red. And as you would expect, we get a great correlation for both global and thresholded PCC. And this is really important because it shows that our ability to generate negative correlations isn't gained at the expense of our ability to generate positive correlations, so we can still get good positive results. This sample shows HeLa cells labelled with Herxt, which labels DNA, and histone H2A conjugate to GFP, which labels the nucleosome. Now, given that DNA and nucleosomes are both component of chromatin, we should see a good correlation. Now our thresholded result is really high, 0.668, whereas the global result is much worse at 0.228. So we're seeing our global correlation being diluted out and lost, whereas our thresholded good correlation is preserved. And that concludes the presentation. I'd just like to thank Chris Guerin and Sam Noppen at the VIB in Ghent for their help with the imaging and for the validation of this technique. Thank you.